In this lesson, we are going to talk about center of mass, and we're going to focus specifically on one-dimensional and two-dimensional objects. Now, when we think about the center of mass of a thin rod or a wire, and we're talking about one dimension first. So here's our thin rod or a wire. This is called a fulcrum, and that's the point in which this will pivot. So you want to think about this as like a teeter-totter at the park. When you put two masses on it, then the distance from the center, and please keep in mind that the fulcrum is not always in the center, but if you come out from the center, then that distance is d1, or in the formula is called x1. Here's our mass 1, and then our mass 2, that's this, and then the distance that comes out this way from the center is d2, or in the formula it's called x2. Now, in this specific example, we have two masses. This pattern can continue if you have more than two masses. This here, in the formula, that was just me being lazy. This stands for center of mass. The symbol that we use for that is x bar. This top part is called the moment. This down here is going to be the total of all the masses added up. In general, if you have n masses and you have n points from the center, the distance from the center, then in general, the moment is going to be defined as taking each of those masses and multiplying it by the corresponding distance from the center, and then we add them all up. Then we get the center of mass by taking the moment and dividing it by the total mass. And that's defined right here. The total mass is just adding up all the masses. Okay, so let's look at our first example. Finding the center of mass of objects along a line. Suppose 4-point masses are placed on a number line as follows. So we have the mass in kilograms, that's our m's, and then the distance from the origin is our x's. It says find the moment of the system with respect to the origin and find the center of mass. So to find the moment, the first thing you want to do is multiply all the masses with the corresponding distance from the center, and then you want to add them up. So that's what I did here. I took 30 times -2, because that's this mass with this distance from the center. Then I took 5 times 3, that's this times this, and I went ahead and did that for the last 2 points as well, and then added it all up, and I got that the moment was -30. Then to find the center of mass, you want to take that moment and divide it by the total of all the masses. So the sum of the m's, that's this, in the denominator, I added up with 30, 5, 10, and 15. And when I did that arithmetic, I got -1/2, which tells us that the center of mass is 1/2 meters. These units are in meters, so we want to make sure we're consistent. And because this is negative, that means it's a 1/2 meter left of the center or of the origin. So now we're going to generalize this idea and extend it from one-dimensional to two-dimensional. So when we look at a mass, xy coordinate plane, the distance from the origin is going to be defined as an ordered pair, x, y. Now going down to look at how we find the center of mass, we're just extending the idea that we did before, where we take the mass and we multiply it by distances. But now that we're looking at it in two-dimensional, we have to keep in mind we want to find the moment about the x-axis and then the moment about the y-axis. So we're going to have to find an ordered pair as your center of mass. So as normal, you are going to find your total mass by adding up all the masses. But then to find your moment about the x-axis, you're going to take all of your masses and multiply them by the corresponding value of y. Then to find your moment about the y-axis, you're going to take all your masses and multiply them by the corresponding value of x. And then to find the ordered pair for your center of mass, for your x-coordinate, you're going to take your moment about the y-axis and divide by your total mass. And then for your y-coordinate, you're going to take your moment about the x-axis and divide by the total mass. So let's look at an example of this. Finding the center of mass of objects in a plane. So we have three masses placed in an xy plane, and it says here, assume the coordinates are given in meters. So we have a 2 kilogram mass placed at -1, 3. We have a 6 kilogram mass placed at 1, 1. We have a 4 kilogram mass placed at 2, -2. So to find my moment about the y-axis, I'm going to take all my masses and multiply them by the corresponding value of x's. So I'm going to take 2 times -1, 6 times 1, 4 times 2. I'm going to add all of that up and I get 12. So that will be my my, my moment about the y-axis. Now I'm going to look for my moment about the x-axis, where we do the same thing, but we multiply by the corresponding value of y. So I'm going to take 2 times 3, 6 times 1, 4 times -2. I'm going to add all of that up, and I get 4. Now, to find the total mass, I just have to add up 2, 6, and 4. That's my total masses here. That will give me a total of 12. So now to find the x-coordinate of my center of mass, I'm going to take my my, that's this up here, it got cut off a little bit. Let me scroll up. So I'm going to take my my and divide by my total mass, which is 12, and I get 1. To find my y-coordinate of the center of mass, I'm going to take my mx and I'm going to divide by the total mass, and I'm going to get 1/3. So the center of mass for this system, where I would have my balancing point, would be 1, 1/3. And of course, we have our units here in meters. Okay, now in the next topic of this lesson, we're going to talk about center of mass of thin plates. So up until this point in the lesson, we've talked about center of mass for a line or a plane, but with discrete points, so specific places where these masses lie. Now, if we consider if the mass is distributed continuously in a two-dimensional plane, which is sometimes called a sheet, this sheet is also called a lamina. So you have continuously distributed mass in this sheet called a lamina. And now if you're looking for the center of this lamina, specifically the geometric center, that is called a centroid. Now, if the mass is distributed uniformly in this sheet, then the centroid, which is the geometric center, will also be the center of mass. So in this next idea, it says it's called the symmetry principle, and it's pretty self-explanatory. It just says if you have some region, some two-dimensional object in the xy plane, then, and if you're looking for the centroid, if it's symmetric about some line, so let's say the line is right here, then the centroid should be on that line of symmetry. So that's basically what this theorem is stating. Now, to find the center of mass of a thin plate, To find the total mass, you take the density and you integrate it over the interval that you're interested in, and you integrate f of x dx. Okay, and then to find your moments about the x and y axis, these are your formulas that you would use for that. And then again, to find your coordinates, your xy coordinate, to find your x, you want to take your my and divide by the total mass, which you get from up here. And then to find your y coordinate, you take your mx and you divide by your total mass, which again, this would be your total mass. All right, so let's look at our example. So it says R is going to be the region bounded above by the graph of the square root of x and below by the x-axis over the interval from 0 to 4. And we want to find the centroid of the region. So we need to find our mx and our my and then our total mass. These are the three things we need to find. Now, according to the formula above, to find the mx, we take our function and we square it, and we divide by 2, and then we integrate that over the interval that we're interested in and multiply it by our density. Now, the problem doesn't tell us what the density is, but you'll see here in a little bit that that's not going to matter. So when we integrate this, keeping in mind that this is some constant value, so make sure you carry that with you, you're going to get that the integral itself is 4, but then when you multiply it by your density, that's going to be rho times 4. Then, for finding your moment about the y-axis, you take your density, and then you multiply it by the integral from 0 to 4 of x times your function. When we do that, we get that the integral itself is 64 over 5, and then when we multiply it by rho, we get rho times 64 over 5. Then to find the total mass, we take the density and multiply it by the integral from 0 to 4 of our function. And when we do that, we get rho times 16 over 3. Now, to find the center of mass, to find the x-coordinate, I take my moment about the y-axis and divide by the total mass. And so we got the moment about the y-axis was 64 over 5 times rho, so that's this here. And then the total mass we get is rho times 16 over 3. And this is why the density doesn't matter as far as us knowing what it is, because when we divide, this just becomes rho divided by rho, which is 1. And so we end up getting, for our x-coordinate, 12 over 5. Now we do the same thing for our y-coordinate. We take our moment about the x-axis, divide by our total mass. So we get rho times 4. And then we divide it by the total mass, which we got was rho times 16 over 3. This divided by this is 1, so that goes away, and I'm left with 3/4. So the geometric center is going to be 12/5, comma 3/4, which is approximately right here if you want to visualize that. This topic in this section that we're going to talk about is finding the center of mass of a lamina when it's bounded by two functions. Okay, so to find the total mass, you're going to use this formula here, where you take the density and you multiply it by the integral from a to b, and then you subtract the two functions. So it's the top function minus the bottom function. Then your moments about the x and the y-axis are defined here. Here's my moment of the x-axis defined here. You square each of the functions individually, find the difference, multiply by 1/2, and then you integrate on your interval of interest and multiply it by rho. And then for your moment about the y-axis, you find the difference in the functions, multiply by x, integrate that from a to b, and then multiply it by rho. And then to find the center of mass as an ordered pair, Then you're going to take for your x-coordinate the moment about the y-axis divided by the total mass. And then to find your y-coordinate of the center of mass, you are going to take your moment about the x-axis and divide by your total mass. Let's look at our example for this. Finding the centroid of a region bounded by two functions. So we have the top function in blue, which is f of x, that's 1 minus x squared. And then the bottom function is just a line, x minus 1. So to find our moment about the x-axis, we need to take rho times the integral. Now we're doing this from -2 to 1 because this is where it's bounded. Now it doesn't tell you in the problem where it's bounded, so you'll have to do a little bit of work if it doesn't tell you where it intersects by setting these two equal to each other. It's bounded here and it's bounded here. So we're going from x is -2 to x is 1. So that's the interval that we're interested in. So to find our moment about the x-axis, we're going to take rho and multiply it by the integral from -2 to 1. That's our interval of interest. And we're going to square each of those functions and then subtract them. So that's what we get here. But when we clean it up, we get this polynomial here, x to the 4th minus 3x squared plus 2x. I'll let you guys do the intermediate steps. I'm sure you guys know how to expand this. Then once you integrate and you find your answer for the integral, you're going to get -27 over 10, and that's multiplied by rho. And then you're going to find your moment with respect to the y-axis. You're still doing it over the same interval from -2 to 1. You multiply that integral by rho, and what you're going to integrate is the difference in the two functions times x. This is what you have in the brackets when you subtract the two functions, making sure that the order is important. You want the top function to be first. And then when you subtract that, you multiply it by x, you integrate from -2 to 1, and multiply it by rho. When we clean up that big mess, we get rho times -9 over 4. So we just found the moment about the x-axis, the moment about the y-axis, and then now we have to find the total mass. So you find the total mass by taking rho times the integral from -2 to 1, and you subtract the two functions, the top function minus the bottom function. When we integrate that and multiply by rho, we get rho times 9/2. So now to find the ordered pair for your center of mass. To find the x-coordinate, you take the moment about the y-axis divided by the total mass. So we're going to take rho times -9/4 and divide it by rho times 9/2, because this is the total mass that we just found. And when we do that, we get -1/2. Then to find the y-coordinate of the center of mass, I take my moment about the x-axis and divide it by the total mass. When we found the moment about the x-axis, we got that rho was -27 over 10. And then, of course, our total mass we got was rho times 9/2. And when we divide this, we get -3/5. So the centroid for the bounded region between these two functions is -1/2 and -3/5. And if we look at that up here, it's going to be right somewhere in here.